In the current module, we will discuss the fitting of a multiple linear regression as compared to a simple linear regression where we have one dependent variable and one independent variable. In case of multiple linear regression, we have one dependent variable which depends on two or more than two independent variables. So, in this module, we will discuss how we can write down a module for such a regression model, and we will look at the assumptions, and also we will discuss the interpretation of the regression parameters that are involved in a multiple linear regression model. This module is dedicated to Introduction to Multiple Regression Part 1. Here is a brief overview of this entire lecture. I will begin with a description of the multiple linear regression model as compared to the simple linear regression. I will discuss the challenges that we encounter in multiple regression model. Then I'll discuss the model assumptions and a few terminologies that we come across while fitting multiple linear regression model to a dataset. I will discuss an example of fitting a multiple regression model using R code with the help of a dataset called kids data. And before rounding up this lecture, I will discuss the multiple correlation and partial correlation in the context of multiple linear regression. According to the simple linear regression model, we know that the conditional mean value of the dependent variable for given values of explanatory variable x is given by beta naught plus beta 1 x, where beta naught and beta 1 are called the regression parameters or the coefficients. The multiple regression model differs from the simple regression in terms of the explanatory variables. As we have just seen in the simple linear regression model, there is the presence of only one predictor variable x. In multiple regression model, there are two or more predictors in the system. In general, a model which has p explanatory variables x1, x2, xp and y is the response variable, then expectation y given the vector of predictors x is given by beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp, where beta naught, beta 1 up to beta p are called the regression coefficients and x1, x2 and xp are the p predictors. Now there are a few challenges that we meet with while trying to fit a multiple regression model to a dataset. The first of which is the choice of best model. As I have just explained, in case of multiple linear regression, we have a number of predictors, usually two or more, in which case, which set of predictor best describes the model is the question that is posed to us. So, when we try to fit a multiple regression model, we need to make sure that all the variables, the predictor variables that we are using, are significantly contributing to this multiple linear regression model. Next, interaction between predictor variables is also one of the challenges that we meet with in multiple regression. The model that I have just shown you does not contain any interaction between the predictor variables. However, in certain cases, it has to be taken into account because there is reason to believe that there's interaction between the predictor variables that we are using. A third difficulty that we come across in multiple regression is the difficulty in visualizing regression relationship. In case of simple linear regression model, we have seen that before we fit the model, we usually create a scatter plot between the predictor variable and the response, and by looking at the shape of the plot, we can determine whether there is a linear relationship between the two variables. However, in case of multiple linear regression, there's multiple predictors and we run out of dimensions to create readable plots that can be interpreted easily. And finally, the last challenge is the difficulty in interpreting the model. The coefficient estimates are modified every time we add a new predictor to a multiple regression model. Hence, interpretation of the regression equation becomes problematic. Now, there are a few model assumptions made before we try to fit a multiple linear regression model. The first model assumption is that relationship between the independent and dependent variable have to be linear. The second assumption is of normality. The model requires that the errors in the model have to be normally distributed. The third assumption is of multicollinearity. Multicollinearity occurs when the independent variables are not independent from each other. That is, predictor variables x1, x2, xp that we have seen in the model before, if we arrange them in a matrix form, this matrix has to be of full rank. The absence of multicollinearity is a very important model assumption in case of multiple linear regression. Fourth, we have homoscedasticity, which means the error variances must be constant. We assume that the error is normally distributed with mean 0 and variance sigma square, and the homoscedasticity assumption assumes that the error variance must be constant. Finally, the last assumption is that the absence of correlation between consecutive errors. Now, as a formal definition of multiple regression model, the population regression model of a dependent variable y on a set of k independent variables x1, x2, xk is given by y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta k xk plus epsilon, where beta naught is the y-intercept of the regression surface and each beta I for I equals 1, 2 to k is the slope of the regression surface, sometimes called the response surface, with respect to xi. Now, based on this model, let me walk you through the assumptions of the multiple regression model one more time. Based on this model, the errors, epsilons, follow normal distribution with mean 0 and variance sigma square. There is absence of heteroscedasticity, which means there is constant error variance. There is absence of multicollinearity. The predictor variables x1, x2, xk are independent of each other, and there is no correlation between the predictor variables. Now, some key terminologies related to multiple regression model. The intercept, the term beta naught in the model is called the intercept, and the predictor, the list of explanatory variables upon which y depends. In the previous model, it was x1, x2, xk are the predictor variables. Now, transformation of predictors. Oftentimes, when fitting a multiple regression model, we need to transform one or more of the predictors to create new terms. For example, in the previous model, we can use the logarithm of x as a new predictor variable. Or we can use polynomials. Sometimes we fit curved functions by including polynomial terms in the multiple regression model. For example, if we have two predictor variables x1 and x2 in a model, such that x1 might be one of the predictors and x2 can be the other predictor where x2 is the square of x1. Hence, we can use the multiple linear regression model to fit polynomials. We have interactions and other combinations of predictor variables, sometimes included in the multiple regression model. Sometimes, if there is evidence that the interaction between predictors is significant, then we combine several predictor variables in the model to give us interaction terms. And finally, we have dummy variables and factors. When predictors are categorical with two or more levels, they are called factors and they are included in the model using dummy variables. Dummy variables typically have only two values, often 0 and 1. 1 indicating the presence of a particular observation and 0 indicating the absence of it. Now, after discussing the multiple regression model and the assumptions of the model and key terminologies in connection with the multiple regression model, let me show you an example of fitting multiple regression model to the kids dataset. In this dataset, as an example, we consider following data from Kleinbaum, Kupper and Miller text on regression analysis. These data show weight, height and age of a random sample of 12 nutritionally deficient children. If you remember in the module on simple linear regression, once we have data on response variable and one single predictor variable, we usually create a scatter plot or we compute the correlation coefficient between the two variables to first check if there is any evidence of linear relationship between the two variables. Similarly, in case of multiple regression, once we have the kids dataset in our hands, before fitting a multiple regression model, we would like to create the scatter plot, which is Scatterplot matrix in this case, and find the correlation coefficient between the variables involved in this dataset. The Scatterplot matrix can be created using the plot function, but before that, using R, we first read the variables, the three variables into R as weight, and we read the variables for weight, height, and age and put them in a data frame and name it kids. Next, using the correlation function COR function in R, we obtain the correlation coefficients between the predictor variables and also each of the predictor variables with the response variable. After we use the correlation function, we obtain as the R output the matrix of correlation coefficient between weight, height and age. From the output, we see that the correlation coefficient between weight and height is 0.8142, which is a very high positive correlation coefficient indicating a positive linear relationship between weight and height, and the correlation coefficient between weight and age is 0.7698, which is again a high positive correlation coefficient indicating linear relationship between the two variables. Weight here in this dataset is considered as the response variable and height and age are the two predictors. The scatterplot matrix shows that both the explanatory variables height and age are strongly linearly related to the dependent variable weight. However, we can also see that the two predictors height and age are strongly linearly related to each other. And the strong linear relationship between weight and between height and age is also supported by the fact that the positive correlation coefficient values in the correlation coefficient matrix. Now, after we have looked at the scatterplot matrix and the correlation coefficient between the variables, there is reason to believe that there is a linear relationship between the predictor variables and the responses. So now I will show you the fitting of a multiple linear regression model to this dataset using the LM function in R. We will fit two models in succession, first with only height as a single predictor variable because the correlation coefficient between height and weight is higher than the correlation coefficient between weight and age. And in the second model, we will now add age as the second predictor variable. So here is the R code for fitting the linear regression model to the kids dataset. The first model, called model 1, we use the LM function in R to fit a model between weight and height, where weight is the response and height is used as the predictor variable. And the second model is again fit using the LM function, but we fit the model using weight as the response and height as well as age as the two predictor variables. Then using summary, we look at the output for the two models. The first output is the summary of fitting model 1, which only has one predictor variable height, and the second model where we use height as well as age as the two predictor variables. And we fit this model using LM function as well. So using summary of the two models, we will look at the R output and see what the estimates of the parameters are and how significant these predictor variables are. First, we have the summary of model 1 where there is only one predictor variable, height. The output gives us the estimates of the intercept and the slope parameter along with their standard error and the corresponding p-values. If we fix alpha at 0.05, we can compare it with the p-value corresponding to the estimate of coefficient of height, and we see that height as a predictor variable is very significant in the model. And next, when we look at the model where we have used height as well as age as the two predictor variables, keeping alpha equals 0.05 as our level of significance, if we look at the p-values corresponding to the coefficient estimates of height as well as age, we can see that height is still a significant predictor, however, age is not. In the output, we can clearly see that in both the models, the p-values corresponding to the coefficient of height suggest that height is a significant explanatory variable in the model. However, in the second model, where we add age as the other predictor, we can conclude from the p-value that age is insignificant and can be removed. We can also compare the two models using ANOVA function in R. In order to do that, we first fit the two regression models. First, where there is only one predictor variable, height, and second, where height and age are both used as predictor variables. We can also compare the two models that we have fit using the ANOVA function in R. In order to do that, we will first fit the two models using the LM function in R, the first of which is the model using only height as the predictor variable, and the second is where height and age are both used as predictor variables. And then using ANOVA function on model 1 and model 2, we can compare the two models. As the R output, we are given the analysis of variance table, which contains the F statistic and the corresponding p-value for comparing model 2 with 1. Using this ANOVA table, we compared the two models, the model involving height and the one involving height and age. The p-value from the ANOVA table shows that there is good reason to use height as an exploratory variable. However, there is no reason to use age as the other predictor variable, because from the ANOVA table we can see that the p-value is higher than alpha equals 0.05, which suggests that the second model is not a significant improvement over the first, where the first model just contained height as the only one predictor variable. After discussing the example of fitting a multiple linear regression model using the LM function in R, let me discuss two important concepts in context with multiple regression models. The first of which is multiple correlation. The correlation between the predicted values of the dependent variables y and the observed values is called the multiple correlation coefficient and is almost universally denoted with the value R. The multiple correlation coefficient is always positive, and R square is the percentage of variance in y accounted for by the predictors. For reasons of clarity, however, we sometimes denote the squared multiple correlation coefficient as R square y given x1, x2, and this indicates that x1 and x2 are the variates used in the regression equation. And next we have partial correlation. If y is the dependent variable and x1, x2, xk are the predictors, then the partial correlation coefficient is a correlation coefficient that describes the behavior of y and x1 when x2, x3, xk are held fixed. The partial correlation coefficient between y and x1 holding x2, x3, xk fixed is denoted by lowercase r x1y dot x2, x3, xk. Suppose we have three variables in our dataset where y is our response and x and z are the two predictor variables, then the partial correlation coefficient can also be written in terms of simple correlation coefficients given by the formula r xy given z equals r xy minus r xz times r yz divided by square root of 1 minus r square x z times 1 minus r square yz. So in this module we have seen how we can fit a multiple linear regression to a data set where we have one dependent variable which depends on several independent variables. We have looked at the interpretation of the regression coefficients in case of multiple linear regression as compared to the interpretation of the regression parameters for a simple linear regression. And we have also illustrated the fitting of a multiple linear regression model using a data set and using R.